Our next speaker is Professor Saurabh Singh, and he will continue his lectures on delta methods. His lecture will not be 1.5 hours, but maybe a little over 1 hour. So we will not have a break after 45 minutes.
Recall. We are proving the formula. And heat from the delta n is some CQ by Q square, summation Q from 1 to infinity. And summation of A modulo Q star, E of An by Q, H of Q by Q, and N by Q square. For the some nice weight function h of xy, we will derive the sum formula for this h of xy. But we have already proved this one, but let's quickly recall how the proof goes. We start with function. So we say that integer n is 0 if and only if it is divisible by all integers. This is one of the basic properties of a zero integer. Is 0, it is divided by all integer. Enough to say that a non-zero integer only has finitely many divisors. Okay, now we take the function w naught, exponential of minus 1 upon x square if modulus of x is less than 1, and we take 0 or mod x to be bigger than or equal to 1. So this is a very nice function, infinitely many time differentiable. And function as well as derivative, they satisfy, they are bounded. Okay. Now this w naught x is supported on open interval minus 1 to 1. So we want something move away from the point 0. For that we define w of x. Okay. For that, let C naught is the constant. This fantastically convergent integrals given by w naught x dx over r. And we define function w. We define w of x to be 4 divided by C naught and w naught of 4x minus 3. Okay. Now w naught is supported on minus half to half. So we require this one to be 4x minus 3 to be lie between 1 and minus 1. This is equivalent to saying that x lies between half to 1. So w is supported on we will see why we are moving from 0 to half to 1. Okay, we define delta n. Okay, so we will use other property if d is divisor of n, then so is n by d. So if d divides n, if and only if n by d also divides n. So we define the symbol delta of n. This one is summation q divisor of n, w of q by q. So we will fix some real number q, which is bigger than or equal to 2, a fixed real number. With respect to that capital V, we define capital delta of n is w of n minus w of modulus of n by q by q. Okay. If n is not equal to 0, then we obtain that divisors match up here. So q is divisor, so does n by q. So both they cancel. We obtain that delta of n to be 0. Now, the case if n is 0, if n is 0, then this function is gone because w of 0 is 0. So we obtain delta of 0 to be summation of q divides 0, w of q by q. And this is same as summation q from 1 to infinity, w of q by q. Okay. Now we have the Poisson summation formula. It says that if f is belong to the Sorge class, it's true for more general function, but for this construct for the Sorge class, then you have summation n belonging to z f of n is same as summation of n belonging to z f at n, where f at y is given by integration over r f of x e of minus of xy dx. So we apply this Poisson summation formula for this function. So this one is given by delta of 0 is summation. Okay. We take n belonging to 0, n belonging to z, w hat of q by q. So that's nothing but summation of q belonging to z, integration over r, w of u by q, e of minus nx dx. Now this is same as, just change the variables. This is same as q times summation q belonging to z, integration over r, w of x, e of minus n, u of x dx. A q. Yeah. What? We will restrict, yeah, that will restrict the range for this is parameters you can choose at your choice. So the choice for this capital Q will comes once we study the function of h of x, y. Okay. Now the term when n equal to 0, this gives you q times integration over r w of x dx plus big O of q times modulus of integration over r w of x e of minus nqx dx. Okay, and we have seen, you've seen that we have just normalized wx in such a way that integration over r w of x is 1. So that's give you q. Now here apply, okay, there is we are something missed, summation of n from 1 to infinity. Yeah, summation n not equal to 0. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Now, if we apply the integration by part, if you differentiate this function, integrate this one, for once you will get n by q in denominator. If you apply integration by twice, you will get n by q whole square in the denominator, and for n many times, you will get n by q in the denominator. So that will be given by q, big O of q, summation of n not equal to 0, 1 by nq to the power n. Now just apply integration by parts n many times. So that one you can write as q times cq, where cq is, I will take a cq inverse. Cq inverse is 1 plus big O of n of q to the power minus n. So we'll get 1, and error term is very small. So we put together as in this combination, we obtain that this delta n is nothing but cq by q, just multiply by q inverse and by cq, and summation of q divides n, w of q by q minus mod n by pq. Now we will detect this condition q divides n by using the additive character. So this is given by cq by q and summation of b modulo q e of bn by q divided by 1 by q, and then you have to take summation q from 1 to infinity and w of q by q minus w of modulus of n by qq. By the way, this also serves as a delta method. This is called the trivial delta method. We will see it. This is same as this function, summation of b modulo q e of nb by q. This also serves as a delta method called the trivial delta method. This gives a condition that this is non-zero if n is congruent to 0 modulo q. And if you choose q in such that if you q is bigger than n to the power 1 plus epsilon, then this gives you exactly 1. If n is 0 and it is not, so this will be delta n for q bigger than n to the power 1 plus epsilon. That's called the trivial delta method. I think Keshav will talk about this one. Yeah. Now here we want to make this one to be free of GCD. So let J is the GCD of B and Q. So you can write Q is equal to J times L, B is equal to J times A. Now here we will get A, GCD of A and L to be co-prime. Once you divide by the GCD, the remaining thing will be co-prime. So this is nothing but CQ by Q, summation of J, summation of L, vary from 1 to infinity, 1 by JL, summation of A modulo L, but now varies over residue classes with coprime with L, E of AN by L, and the same function W of Q is JL by Q minus W of mod N by JLQ. So I will take the GCD things, they are on average behaves like 1. So I will take a JSON inside. So that one I will write as CQ by Q, summation L from 1 to infinity. So I'll take 1 by L and summation of A modulo L star, E of AN by L, and take JSON inside, summation J from 1 to infinity, 1 by J, W of JN by Q minus W of modulus of mod N JL times Q. So there is 1 by factor is here. So what I'll do? I divide by Q here. I multiply by Q here. So this one I can manipulate as J by Q times Q square. So this one, so now I can take this Q outside. So this will be CQ by Q square. Now change L with Q. So this will be Q from 1 to infinity. Yeah, so that's what I'm doing here also. Summation of L from 1 to infinity, summation of A modulo Q star. I'll do L by Q. This factor I will do here. L by Q and Q. I will keep J as it is. Summation of A modulo Q star, summation J from 1 to infinity, 1 by J, W of J Q by Q minus W of mod N by Q square. And J L by Q into Z. So this function I will call it H of Q by Q times mod N by Q square. So mod N by Q square with some factor here H of XY is given by summation over J 1 by XJ W of JX minus W of mod Y by JX. Okay. So we have obtained expression for delta symbols in these forms where H of XY will be some smooth function. We will prove that H of XY is bounded by 1 by X, and we will prove some property for H of XY. Okay, any questions so far? The main property for H of XY, which we use when apply the circle method, I will just list it. Theorem H of XY is 0 if X is bigger than 1, X is bigger than 1, and mod Y is less than X by 2. A, if X is less than 1, so note that X is always positive, so X is always bigger than 0. If X is less than 1 and modulus of Y is less than equal to X by 2, then H of XY is constant with respect to Y, taking value, and value of H of XY is bounded by X inverse. Also, the derivative del to the power m by del x to the power m H of XY, if you multiply by x to the power m, this will be bounded by 1 by x. The part B, if x is less than 1 and y is bigger than x by 2. Then in that case also H of XY is also a very nice and smooth function. Smooth function. And its derivative satisfies del to the power m plus n by del x to the power m del y to the power n H of XY. So multiply by x to the power m and y to the power n. It's also derivative satisfy bound 1 by x. So in totality, h of x, y is smooth functions and bounded by small q by capital Q. So the range for q, where we have taken q from 1 to infinity in the formula, I think I just erased. You can restrict the range for small q to be the capital Q. Otherwise, the function will be negligibly small. Okay. So let us prove this. So before going to the proof, I will just use one simple fact. So we have the W function and its derivative. This one is bounded by 1. Not only that, we also have x to the power alpha Wx is bounded by 1. Okay. Because the support for W is lie between half to 1. So only the point where this matters is x lies between half to 1. Otherwise, its value is 0. That is why we have moved away from the point 0. Near 0, it might create problem, but we are not in the range of 0. That's why we translate our function from -1 to 1 to half to 1. Okay. Lemma. For any alpha belonging to R, summation over J 1 by Jx 1 by J W of J alpha is bounded by 1. Maybe I have to see R and summation over J 1 by J W of alpha by J is also bounded by. It's not only that, you can prove that its derivative is also, its kth derivative also satisfies this bound. Okay, proof. The range for J, where this function is non-zero, we want that J times alpha to be lies between 1 and half. It says that J varies to 1 by 2 alpha, 1 by alpha. This one is summation of 1 by 2 alpha less than J less than 1 by alpha, 1 by J, W of J alpha. This one is less than, so Wj is bounded by 1. And for the upper bound, you can put the maximum of, yeah. So less than 1. For upper bound, you can put, yeah. And 2 alpha. And total number of points in summation is given by 1 by 2 alpha. So that's one. Similarly, for this one. So this one is non-zero if alpha by J lies between half to half and total number of points for J is given by some range. You can also prove that this one is non-zero and its upper bound is bounded by 1. Now using this lemma, let us prove the part A and B. Yeah, for k equal to 0 and for derivative is also, because Wk is also nice smooth function supported on half to 1. Yeah, so Wk, the kth derivative is also nice function supported on half to 1. The first part, it says that if x is bigger than 1 and y is less than x by 2. In that case, we have to show that function h of xy is 0. Just recall what is definition for the function h of xy. H of xy is nothing but summation over j 1 by xj w of jx minus w of mod y by xj. Now, if x is bigger than 1, if x is bigger than equal to 1, then j times x is also bigger than equal to 1. So this function is already 0 because support of w lies between half to 1. And if y is less than x by 2, so y by, yeah. If modulus of y is less than x by 2, so this implies that modulus of y by jx, which will be less than modulus of y by x, which will be less than half. So both functions are 0, hence all summands are 0. Okay, now come to the part A. Part A, we are in the range x is less than 1 and y is less than equal to modulus of y is less than x by 2. In that case, so we can always write h of xy as h1 of xy minus of h2 of xy. So h1 is given by this, h2 is given by the summons of all these things. So in this case, we have h2 of xy is 0, and we obtain that h of xy is given by summation over j 1 by xj w of jx, which is independent of the point y. This is the statement. This is constant with respect to y, and we can prove, apply that lemma, this value is bounded by 1 by x, you can take out, then summation over j, w of jx is bounded by 1. Okay. By the previous lemma, just take x out, summation over 1 by j, w of jx is bounded by 1. And similarly, its derivative. What is the derivative with respect to x? Note that del power m by del x to the power m w of jx is nothing but j to the power m, mth derivative at the point j of x. Now here argument is j of x, here is x. What we do, we multiply by x to the power m and take x to the power minus m. Just to do some adjustment, and we use the fact that x to the power alpha and w, mth derivative of alpha is bounded by 1. That is bounded by x to the power. Okay. So we are in time and time again, we are using the fact that x to the power alpha, any derivative of w with respect to x, this one is always bounded by 1. That is the point we are moving away from the point 0. We can avoid this thing can go to 0 when this one is like a positive power, so we are going this one. So since we are moving away from 0, so this is fine. And we are taking x to be in compact interval, which is away from 0. So using this one, we obtain del to the power m h of xy del x to the power m is nothing but Now you have to apply the Leibniz rule. So x to the power minus m will be coming from this derivative times 1 by x. So you have to differentiate x at every point x. You differentiate x, you will get 1 power. Similarly, if you differentiate w, you will get 1 power of j. But to manage that power of j, you have to multiply by x and divide by x. So every time you will be getting power of x in the denominator. So that is the fine. Now let us prove part B. Proof of the part B exactly similar. Now we are in the range x is less than 1 and y is bigger than x. Recall that h of xy is summation j 1 by xj w of jx minus w of y. Now, the proof for the derivative with respect to x will go exactly as in the case of the part A. Let me just do it for our sake. J w of gx power m, and every time you will get power of g out by gx minus of, and for this you will get mod y by. And use that lemma. So all these things you can just bound it by. So this will give 1 by x, and to manage this one, multiply by x to the power m, and also you will get x to the power minus m. Similarly, if you differentiate with respect to y, this will be vanishing. So you will be getting power of x in the denominator for every differentiation. So that's why you will get power of x to the power minus n if you differentiate with respect to y. So you will prove that derivative satisfy that bounds x to the power m minus n and minus 1. Now we saw that the function is small if x is quite small with respect to y. So let me just state the next lemma. Theorem. Del to the power m plus n h of xy del x to the power m del y to the power n. This one is less than x to the power minus of 1 minus m minus n x to the power n plus minimum of 1 mod of x by y is whole power n. Yeah, this shows that if your x is very small in comparison to y, then minimal will be this one, and so this will be very small. Sum if x is little o of 1, minimum of 1 and y. So how to prove this one? Yeah, if x is bigger than 1, x is bigger than 1, or x is bigger than mod y, x is bigger than mod y, then proof follows from the previous lemma, because all these things are positive, which is bigger than 1, and this we have already proved. Then to prove previous lemma. because all this Scottish will be bigger than 1, and we have already proved that derivative satisfies this bound. Now we can assume that x is less than 1 and mod y. Now to prove this one, we have to apply the Euler-Maclaurin summation formula. I suppose all of you know what is this summation formula. We can assume this one. Yeah, it says that suppose f is infinitely many time differentiable function. Then it relates summation a less than n less than equal to b f of n with the integral a to b ft dt plus a minus floor a minus half f of a minus b minus floor b minus half f of b plus summation k from 2 to n minus 1 to the power k by k factorial fkt and psi k t from t equal to a to t equal to b minus of 1 to the power n integration of a to b nth derivative of f at the point t psi of nt dt, I think by n factorial. Here the psi's are the Bernoulli polynomials. Now we apply this formula to treat the sum 1 by xj w of jx. You see it? Summation over j 1 by xj w of jx. So this one, so support for w, we restrict the j to be interval of length to be 1 by 2x to 1 by x, and then w of xt 1 by xt dt. And there won't be any boundary terms because support of w is lie between and half to 1. So there won't be any boundary term. Minus of minus 1 to the power n by n factorial integration of 1 by 2x to 1 by x pnt and derivative of till to the power n w of tx by tx dt. So we apply that summation formula to the functions wjx by xj. Similarly, for sum involving h2 summation over j 1 by xj w of mod y by gx this will be now from here, j will be varies from integration of modulus of y by x to 2 times modulus of y by x, w of 1 by xt, w of mod y by dx dt minus same thing minus 1 to the power n by n factorial integration from modulus of y by x to 2 times modulus of y by x 1 by xt w of the p and t and derivative del to the power n of the same function w of mod y by tx divided by tx dt. Yeah, p and t I'm taking as I of nt. Yeah, on that nth periodic Bernoulli phenomenon. Now we see that these two main terms they will cancel to each other if we substitute. Yeah, so we want modulus of y by tx as xt. So if you substitute this change of variable with respect to t, so this will be cancelled to each other. So we substitute the change of variable as x times u in second interval. Second integration. Then we will see that the two main terms appearing here and appearing here, they will cancel to each other. They are exactly same. So we are left with, for the function w, we are left with to showing that integral is negligibly small for this one. Sometimes let me just go through this step. Yeah, if we go to this function definition for h of xy, then we have to take this minus this, and with this change of variable, the main term cancel out. So we are left with the error terms. So h of xy is in fact, if you apply the change of variable, this will be x to the power n minus 1, minus 1 to the power n by n factorial integration of half to 1. We want to just put this one tx to be just u. We get raised from half to u. Pn of u by x. No, I think that is fine. There is summand and there is integrand. Nth derivative, yeah. W to the power n u du by u and minus of 1 by x by mod y to the power n minus 1 to the power n by n factorial integration of 1 to 2 Pn of u mod y by x and d by du to the power n w of u by u. And similarly, if you differentiate with respect to x, so you will be getting the power of x in the denominator from this one. And similarly, to manage this one, we have to multiply the power of x in denominator for this one. So for this, just h of xy, x to the power n is already there, below of x to the power n. And for other parameters, you will be getting to manage this Yeah, to manage this one, if differentiate m times, you will getting x to the power minus m and u by x to the power j. If differentiate j many times, 0 less than j less than m. So if for mth derivative, we will be getting power of x to the power minus m here. And from this integral also, you will be getting the power of x to the power minus m. You differentiate with respect to I n many times. So we will prove the lemma what you want. So this one, nth derivative of w of u inverse by u inverse du. Okay. Next time, in the next lemma, I think we will prove that what Binay wants, that if you have some involving minus of x to x, h of xy dy, this is just 1 plus big O of x to the power n minus 1 plus big O of x by x to the power minus n. So here the integral with respect to second variable on average just behaves like 1. Okay. And I think just these two property. And one property for the HV function we used, that if you integrate function f with respect to a smooth function y, note that this right hand side is independent of your choice for the function w what you have chosen. So you can choose any compactly supported function w to start with, because this side does not depend on the function w. This choice of x depends on w, but right hand side doesn't depend on w. So you can choose any w to start with. And the next things which we used, that integration, if you take integration over r f of y, h of xy is respect to dy, what we will obtain f of x plus big O of x to the power n. That depend on. So integral involving the function h is also like behaves like 1. Yeah. Yeah, f of 0. Then, yeah. Yes. This one? Yeah, this one you have to prove this one, not immediate. This one? Yeah. So differentiate this with respect to x. Every time you will getting a power of x. So differentiate of p1u, you will getting 1 by x, and you will replace pn by its derivative. So this derivative is also like we have the that bk prime of x is nothing but k bk minus 1x. They are mth Bernoulli polynomials, and your pkx are nothing but bk of fractional part of. Yeah. So if you differentiate this Bernoulli polynomials, so we'll again end up with a Bernoulli polynomials. So if you differentiate with respect to x, you will be getting 1 by x in denominator and 1 by x outside, and differentiation of this Bernoulli polynomial, which will be again a Bernoulli polynomial that will be bounded. So you will get 1 by x. So if you differentiate m many times, you will get x to the power m in denominator and bounded integral. So you will get x to the power n minus 1 and minus m. Similarly for here, if you differentiate with respect to x, you will be getting the power of denominators and so on. Okay, I think I will stop here. So next time, so I will not prove these these lemma. So next time I will try to do the Peterson trace formula, which will be much easier. Considering to this.
Have any questions for Saurabh? If not, let's thank the speaker once again.